Thank you so much, Kelsey. So we're very excited for tonight's seminar, and we are very excited to have Eliza Diggins and Sienna White to be presenting for us. So this is an open format talk. So please, we encourage you to, if you have any questions, raise your hand, and the speakers will call on you, and they're able to. And if you are on our Zoom, then please use the Q&A function there, and then one of the organizers will read your question at an appropriate time. And so to start us off tonight, we first have Eliza Diggins, where she is a graduate student in astrophysics at UC Berkeley. Her research focuses on using astrophysical systems to explore fundamental questions in physics, including the nature of gravity and the evolution of the universe. Originally from Utah, she earned her undergraduate degrees in mathematics and physics from the University of Utah. Outside of her academic work, Eliza is an avid outdoors enthusiast with a love for whitewater rafting, kayaking, trail running, hiking, and backpacking. She is also a dedicated advocate for the LGBTQIA+ community, working to support inclusion and visibility in both academic and broader public spaces. So please, Eliza, take it away.
Awesome. Well, thank you for that introduction. So I am a computational astrophysicist. So instead of looking through telescopes, which is hard and requires skills, I use computers to simulate things because that seems easier, or at least I thought it would. It turns out that that's a lot of debugging code and being frustrated anyways. But today I'm going to talk a little bit about one of my favorite things that we can do as computational astrophysicists, and that's simulating the universe. And so by way of introducing this topic, I'm wondering if anybody here has heard in the news anything about the Vera Rubin Observatory. I know you definitely have. So the Vera Rubin Observatory is a new telescope that has just recently come online. It's super exciting for a variety of reasons. It's going to do some of the best astronomical science that we've been able to do in a long time. It's the biggest digital camera mankind has ever made. A bunch of exciting things. But recently, it released its first flight images, so some of the very first images it's taken. And this is one of them. And it reminds me of one of the things that got me into astronomy in the first place, which is that not only is the universe full of stuff, it's full of really diverse stuff. Basically, every spot of light in this image is an individual galaxy. And you can see just from looking at it that you've got all sorts of different kinds of galaxies in here, right? Some of them are spirals, some of them are blue, some of them are kind of this goldish color, some of them are smashing together. It's a very dynamic universe. And it's a really interesting question to ask how we get there. How does the universe build these galaxies? Why are some of them blue and spiral shaped? And why are some of them not blue and not spiral shaped? And this is made all the more interesting when you think about the fact that the universe did not used to be anything like this. So about 10 to 13 billion years ago, right in the very early stages of the universe, it turns out there was really not very much going on. And we know this because we actually have a baby photo of the universe, or at least that's how I like to refer to it. So this thing over here, this is the cosmic microwave background, or the CMB. There is so much science and detail that goes into this that it's hard to kind of keep an explanation of the CMB to only 30 seconds. But effectively, it's a picture of the afterglow of the Big Bang. And what you're looking at here are variations of about 1 part in 25,000 in the temperature of this afterglow. So imagine you look out anywhere in the sky and you see this afterglow, and it's exactly the same everywhere you look, plus or minus 1 part in 25,000. Super smooth, and it represents the structure of the early universe. And so what this tells us is that somehow our universe went from this thing that had no structure, no real anything discernible in it, to this very rich universe. And so the question that I broadly find myself interested in is, how do we go from this to this in the course of about 12 to 13 billion years? And it turns out that this is a difficult problem. The physics is really hard, but the good thing is that these days we have computers, and we don't just have computers, we have big computers, very big computers. This is actually the Hazel Hen computer, which I want to know the naming origin of that, but that's a digression. So this is in Stuttgart. This was actually used for some of the simulations I'm going to show you today. But we use state-of-the-art computers like this to answer really interesting questions. I want to talk a little bit tonight about how we do that, and some of the physics that goes into it, and some of the things we learn from that. So to start out, every simulation needs basically two things. You've got to tell the simulation what it's supposed to simulate, so the relevant science, the physical laws that you want to simulate, and then you need to start from something. And we call that starting point the so-called initial conditions of the simulation, right? You got to start somewhere and then let it go. And so in order to set up a simulation of the universe, you need to start the universe somewhere. And the good news is that we have that baby photo, and that's what we're going to use to set up our very first simulation of the universe. So we make a box. It might actually look like this if you want it to look like this. And we're going to fill it with a bunch of neutral hydrogen. So just very basic neutral hydrogen. And we're going to make it ever so slightly bumpy. It's going to be almost perfectly smooth, but it's going to have that same 1 part in 25,000 bumpiness to it, just like the CMB did. And we'll let it go. And we'll add some physics to it. So what do we need? Well, we need gravity. Gravity is going to be really helpful because it's going to pull things together in order to help form structure. Right? That's how galaxies are held together. We're also going to include the expansion of the universe. This is the thing we know happens from observation. So we're going to basically make our box get bigger over time. And then with all of that, we're going to add in fluid dynamics, which is a simple way of saying that we're going to make everything really difficult to do. But basically, this will allow us to have pressure and temperature and all of the various relevant things we care about when we're talking about fluids in the universe. And with just those 3 ingredients, we can let this go. And we can run our very first simulation. And we use a bunch of CPU core hours and a bunch of money. And so that didn't work very well. So this is where you apologize to your boss because you just wasted a couple $1,000s of computing time. And then you scratch your head and you go, why didn't anything happen? This doesn't look good. So, okay, here's the problem. We're actually forgetting a big piece of the puzzle because the universe is not just neutral hydrogen. Actually, it turns out that the majority of the material in the universe is not neutral hydrogen. And so what happens here is that we don't have enough stuff, which is giving us gravity pulling stuff in. And we have too much expansion of the universe, which is making things pull apart. So the moment you start your simulation, everything just floats away from itself. And you get an empty box with no structure, which is super boring and disappointing and makes you feel like maybe you should have considered a different career. So instead, we've got to fix this problem. And the way that astronomers have done that is this thing called dark matter, which sounds fancy. It's basically our way of saying, we don't know, but we need more stuff. So we're going to put it in and we're going to give it a nice name. We'll call it dark matter. And there's an entire lecture to be given about dark matter and all the reasons we know it exists and all the things it could be. All you need to know, as far as this lecture is concerned, is that dark matter makes up actually much more of the matter in the universe than normal things like hydrogen do. And it's kind of edgy, like it's antisocial. So hydrogen interacts with itself via electromagnetic forces and via the weak and strong nuclear force and via gravity. It engages in all 4 of the 4 fundamental forces. Dark matter is kind of like, maybe not, will just do gravity. So that means that it will not have a pressure. It can't bump into itself. All it does is gravity. But it still plays a really critical role. So what we're going to do now is we're going to not tell our boss about the crap simulation we just ran. And we're going to do it with just dark matter. And this time, let's see what happens. So here we are with our initial conditions. And if you look closely, give it a few seconds, you'll notice that it does start to form structure. So what's happening here is that those little bumps in the CMB, those little 1 in 25,000 bumps that we have, are pulling in material. They have more stuff there. They're a little bit more dense. So they have more gravity. So they start pulling things in. And so those little bumps start to pull together and they merge. And the bigger clumps start to pull in smaller clumps and they keep merging in what we call hierarchical structure formation. And this is more or less the foundation of the structure of the universe. And you get something that actually does look very much like this. So let's talk a little bit about the anatomy of that. There we go. So again, here's basically a snapshot of our simulation as we go through, so you have something to reference. But what happens is that this infalling material forms filaments, these sort of web pieces in your cosmic web. And at the edges or at the intersections of all the filaments, you have halos. And those halos are going to be the birthplace of our galaxies. When we go back and we add in hydrogen, that's where those galaxies are going to form. And so the dark matter, even though we have no idea what it is, plays this really critical role in sort of laying the foundation for all the structure in the universe. And in fact, we actually can see this in real life. So this is the dark energy spectroscopic instrument, which is run partially out of the Berkeley lab up the hill. And what they do is they go and they measure the 3D location of galaxies in the universe. And you can actually see that when you look at the 3D map of galaxies in our universe, they are sort of in this web pattern, which confirms our basic hypothesis that this dark matter lays this foundation structure for our universe. So, okay, I promised galaxies, and we haven't seen any galaxies yet, so let's do that. So what we're going to do, we need gas in order to make stars. So we're going to add a bunch of gas to the simulation, and we're going to let it go. And so what you're looking at here is actually a simulation of this process. Down here is your dark matter. So we're looking at one of those big blobs of dark matter, right? This cradle of galaxy formation. And the gas is going to flow along those filaments, and it's going to collide and interact and form your first sort of proto-galaxies. And then those proto-galaxies will continue to merge with one another, forming larger and larger galactic structure. And you can see down here, this is a mock-up of what the stellar light would look like. So when you look at it through a telescope, this is what your stars look like. And you can already see there's sort of this core and then a disk forming around it. And you can see here, we're about to rotate around. And you can really see this actually looks kind of Milky Way-like. That's pretty cool. And that's all just from including gravity, fluid dynamics, and the expansion of the universe. That's already really cool that we're even able to get that far. And you can even see, this major merger, if you look closely, as it starts to come back through, you can see it kind of like pushing stars around. So this is one of the processes that we know has happened to the Milky Way, and in fact is going to happen in a few billion years. We're going to merge with the Andromeda Galaxy, and it will look something like that did, which is really cool. We can kind of learn something about the future by studying these simulations. Now, we can do this many, many times, and people do this many, many times with different initial conditions, and they build libraries of galaxies, which is super cool. But one problem, these are wrong. Oops, very sad. So what's wrong with them? Well, it turns out actually there's not that much wrong with them. Because, we go back, to be honest, these all look pretty good, right? They look like what you'd see on the cover of a space book, right? So, okay, what's actually wrong with them? Well, it turns out that they're just a little too dense sometimes, and they're a little bit too cold. And what happens is when gas in galaxies gets cold, it is allowed to get kind of compressed. And when gas gets compressed, it can collapse into stars. And that's the process of star formation, basically. And so when you have too much cold gas in a galaxy, you get too many stars. Mm-hmm. And so when we look at our, synthetic stars in our synthetic galaxies, and we go and look at real galaxies in the real universe, we actually realize that there are way too many stars in these fake galaxies than in real galaxies. This is sad. They're also a little weird in different ways. The disks aren't quite right. There's some other things. Some very nerdy people decided that these were insufficient. So now we have to go to a bunch of extra effort. So, okay, what do we have to do to fix this? Well, the answer is explosions, which is great because it means pretty pictures. So why do we need explosions? Well, we call this process of fixing this problem feedback processes in general. And effectively, the idea here is that there are various high energy processes that happen in galaxies, like supernova explosions and stellar winds. And then the black hole at the center of the galaxy actually throws off a ton of energy and does some really cool stuff. All of which serves to do one really important thing, which is that it injects energy back into the gas in your galaxy. So instead of getting too cold and forming too many stars, that gas gets kind of reheated and redistributed, and it prevents too many stars from forming all at once. But of course, if you go too far and you blow all the gas out of your galaxy, you won't get any stars. So you have to be very fine-tuned about how you make this process work. And some very smart people have figured out how to do this. And so we now run simulations where we put all of these ingredients into our simulations. And they look something like this. And this is my favorite video in this entire talk. So what you're looking at here is the formation of one galaxy. One of them is edge on, one of them is face on. And every time you see these little explosions going on, this isn't a simulated explosion happening in this galaxy. So think supernova, kaboom, or the central black hole kind of having an ejection event. And what it does is it disrupts these galaxies in the process of their formation. And you'd think to yourself, well, all we're doing is shredding these galaxies. This cannot possibly be the route to good galaxy formation, right? But it actually turns out that this is critical for forming realistic galaxies. And so the material here you're looking at is the gas. The stars behave a little bit differently. And so when you actually pull out the resulting star formation from these simulations, you get galaxies that look like this. And so this is actually from a simulation I use in my research called the illustrious TNG simulations. TNG is the next generation. There was an original illustrious that was wrong. But it actually makes galaxies that are very precisely accurate to our real universe. And we can use that to do all sorts of exciting things. And so as a little bit of a sort of wrap up and a takeaway, all of this is kind of amazing to me. Like, I think maybe it's because this is something I do as a job, but it always shocks me that we can do such a simple set of things and create a universe that looks so similar to our own. But it also allows us to do something really fundamental. And it confronts one of the big challenges in astronomy, which is we can't watch astronomy happen most of the time. Astronomical processes take, at best, years. There's some things that take like days, but like those are very special. Most things take millions or billions of years, so we can't watch them happen. So the fact that we can simulate them is so beneficial and so so useful to modern astronomy. But also it allows us to ask questions about the fundamental processes. And this is what I'm really interested in is we saw that simulation where we didn't have dark matter and everything kind of failed. And so you can learn things about dark matter, about dark energy, about the universe by running these simulations and comparing them to the real world, which I find very exciting. And so if anyone is interested in playing with these, they're actually all available online in an interactive format. So you can go explore these fake galaxies. You can just Google illustrious TNG, it'll come up, it's very cool. And then, feel free to ask any questions, or if you have something that comes up, you can always email me. Okay. Yeah.
That is very, I mean, like there's different atoms and different elements and everything like that. Is there any kind of research on inhomogeneity in dark matter? So like either in density or in character?
Yeah, so I would say that as far as I'm aware, there is an entire field of people who do kind of the theory of what dark matter actually is. And it tends to be these very high energy, like exotic particles. People study like axions and cosmic string, all this sort of stuff. As far as I'm aware, we still really have no idea what dark matter is. We do know that the universe has varying densities of dark matter, right? Like it forms these background structures. But we don't know if it's just one type of particle. Maybe it's a couple types of particles. It's still such a big black box. And it's one of the really fundamental questions in astronomy today. Yeah.
Why are the galaxies flat? Why aren't they like little orbs?
Well, some of them are.
Oh, never mind.
So if we go way back, maybe not that far back. If we go back to the first slide here, you can actually see a number of them are sort of like these ones are orbs, right? Those actually tend to be older galaxies. And so what happens oftentimes is that these spiral galaxies, they're young, they're star forming, they're dynamic. As they hit each other and they collide, they kind of randomize a bunch of things and they throw a bunch of the gas out and then all their stars get old and you get something that looks like this. Now, it is a sort of non-trivial question to ask why disks form like that is a good question to ask an undergraduate student to see if they can really give you a convincing answer, because it's not super trivial. It has to do largely with conservation of angular momentum. So basically that material, if it's spinning, kind of has to keep spinning. And depending on the configuration, it means it flattens into a disk. And that's why we get some disk galaxies. But some of them are orb shaped and some of them are like I don't even know what's going on there. Some yeah.
Do you ever try to go from that photo to the baby photo, like go backwards in time in the simulation?
Yes, so there is an entire field. Actually, there was a talk about this at Berkeley National Lab on Monday that I attended and was very confused by. But there is an entire field interested in using AI to basically go backwards. And the reason we're interested in doing that is that these are super expensive to run. I mean, we're talking like 10 days straight of computing on the best supercomputers in the world. And so it's a non-trivial amount of money, time and effort. You can't just run a bunch of these with a bunch of different baby photos and see what happens. And so we'd love to be able to go backwards, very effectively. That is sometimes difficult, but it's a very broad area of research that we're very interested in. Yeah.
Yeah, those halos, the halos that you mentioned, were those you said they are emerging, are they just emerging in your model, or were they like, do they emerge through observation? And also, if so, is it safe to say that those are range singularities? Or what would you refer to them as?
Yeah, so those halos really do exist. We call them dark matter halos. Effectively, you might imagine the Milky Way disk sort of in your hands. And our halo actually expands much further. It's much larger. But it is more or less just a ball of stuff. It's just a ball of dark
So
matter.
it's not a torus.
No, it's not a torus.
When you said halo, I died.
Yes, it's sort of a weird name for them, right? They're a halo because they surround the galaxy, but they're not a torus. Yeah. So they do form, it is just merging dark matter that forms this sort of spherical-ish thing with the galaxy in it.
And everybody talks about the universal command. Your opinion. Have you heard of the expansive model? You think about it, you need that it's holding weight.
I'm not actually familiar with the expansive model.
It's just basically saying our universe is contracting and expanding. It's not, we don't live in an expanding universe, we live in a universe that has this equilibrium that we can hone in on a measurement, find either one.
Yeah. Well, it is certainly the case that the universe is very dynamic in this expansion. So just because it's expanding now does not actually mean that it expanded forever in the past or that it's going to continue forever expanding. And for a long time, we actually thought that it was pretty definitively shown that it was going to expand and expand and expand. But recent results actually from this DESI experiment that I mentioned are showing that that actually might not be entirely the case. There are some models now where we actually think the universe will basically grow from the Big Bang and then come back to a big crunch at the end. But the exact details of this are actually still kind of up in the air. There's a lot of active research in that area of cosmology still. Yeah.
Is that the expansion? Is that a parameter that goes into your model, or is that something that emerges from the dynamics? So you prescribe an expansion, or you?
Yes. So there are a whole bunch of reasons. Like we have the entire field of cosmology to thank for knowing exactly how the expansion works. But when we go to actually run the simulation, all we really do is we say, okay, make the box expand this much, because we're pretty confident we know how the expansion works. But sometimes it's interesting, like if you change the expansion, this changes quite a bit. And so sometimes we realize that we've been doing the cosmology wrong, and then we kind of have to rethink all of this. Yeah.
Because like universe isn't like to see the universe as a bubble or in a vacuum as an isolated organism, that's kind of the approach, right? To even say that it's expanding, right? We have to isolate it from the greater reality of where it's connected.
Well, so this is actually a conceptual difficulty of
Yeah.
our understanding of the modern universe, which is that in some sense, like the deep mathematics of cosmological theory doesn't really say that we're a universe in anything, but it also doesn't say we're not. It's almost sort of beyond the scope of what any of our physical theory is able to say. And so it has no bearing on prediction, but that's only because our current theories don't really interact with that. Maybe at some point they will, and then, yeah, maybe we know more and things change.
Any last question?
So you said that the original or some of the simulations were like too cold. Like what temperature scale are you talking about?
Oh, okay, this is by far the hardest question. So it's less that they are just uniformly too cold, and more that we get, as the gas falls into the halos, it will get dense. And what happens when it gets dense is that it will radiate away its energy. And it basically gets too cold too quick. And this is one of those things where at some point in my undergraduate degree, I could tell you at what point it's cold enough to form stars, but I do not remember that off the top of my head. But effectively, too much of the gas gets too cold too quickly, and that's the problem, because there's a threshold at which it can collapse into stars, and if too much of it does that, then we're in trouble.
So like is there like a maximum temperature you've like ever seen in your simulation in some local or
Well, infinity, but that's only because I was doing the simulation wrong. Yeah.
This is important. Reason expansive. That it preserved the stick, correct?
I mean, potentially, I don't know. I'm not familiar with the theory.
Just to disregard contracted aspect of it.
I mean, in a theory where the universe did collapse to a point, that is, I think, I'm not a theorist, like I'm not a gravitational theorist. So as far as I know,
You said a point, not agree.
well, right. I mean, whatever it collapses to, I don't think that we have any way of saying what happens afterwards. But again, that might be a limitation of our theory, not necessarily a statement about reality. So we're always learning new things, and as we get better theory, sometimes we realize that our entire conception of how the universe works is a little bit wrong, and we have to readjust. Yeah.
Let's give Eliza another round of applause. And while our second speaker gets set.
Thank you so much, Eliza, for this very informative talk. I
Of
really
course.
enjoyed it. And now it is my pleasure to introduce our second speaker of the night, Sienna White. Sienna is from Boise, Idaho, is currently a fourth-year PhD student in environmental engineering at UC Berkeley. Before starting her PhD, she worked at a San Francisco Actuary Institute working on better understanding and predicting water quality in the San Francisco Bay. And looking forward to your talk, Sienna.
This, so that, oh yeah, I can go back. Wait, so standing here, yeah. Okay, hi everyone. It's really nice of you all to come out tonight. Yeah, my name is Sienna. I'm a fourth year PhD student, and I can try to come up with this really snappy title. Let me try to move my little webinar bubble. Yeah, so today I'm going to talk about San Francisco Bay. I've spent a lot of time thinking about San Francisco Bay, and I think I'm very privileged to get to study a system that we live so close to. And I think it's always fun and interesting to learn a little more about the area right near where we live. So we're right here in downtown Berkeley, where I put this little smiley face. This is a photo of the bay from a satellite, and you're maybe familiar with some of the names of this area. So this whole San Francisco Bay is what we call here. And then we have all sorts of names for the different sub-embayments. So it starts with the Sacramento-San Joaquin Delta. So Sacramento is all the way up here. So we have all this fresh water that comes into Suisun Bay, then San Pablo Bay. We live right across from Central Bay, so you can kind of see where the water goes out at the Golden Gate Bridge. And then South Bay is where we think of San Jose and our whole peninsula. And the key thing to note here is that the Golden Gate is the only entry and exit point for all water in this whole system. And so what goes in has to come in at the Golden Gate Bridge or from any of the rivers in California, and what goes out needs to go out through the Golden Gate. So I think this is just a really fun fact, but if you've ever flown into San Francisco, the airport actually, there's 2 flight paths that come in. And so you've either taken one of these on the east or west, but you'll come in and you'll do this turn right around the Dumbarton Bridge. And if you're really lucky, you'll be able to look out, and they always land planes 2 at a time if they can, if they're operating at max capacity. But you maybe have looked out when you've turned around here and you're coming in for your landing at SFO, and you've seen like the salt ponds in South Bay, or maybe you've seen like a bunch of stuff in the water. And so this has nothing to do with my talk. I just think that's a fun fact. But in general, the main source of water is the Sacramento-San Joaquin Delta. And so this is formed by the confluence of the Sacramento River, which is covered up by that, but it comes up here in the San Joaquin River. And these drain about 2/3 of California's land. So they're really significant water ecosystem, watershed, and then all that fresh water flows. And so if you were to start in a boat here, you'd be in with ocean water. And as you took that boat up towards the Sacramento-San Joaquin Delta, the water would gradually get less and less salty. So there's a transition where it goes from salty water to fresh water, and it's usually right around here. So very different dynamics up here than down here. The water is all salty in Central Bay or South Bay, which if you've ever gone swimming, you would know. And this also means that we have very different characteristics between these 2 systems from a sort of physical standpoint. So in my department, we think a lot about tides and waves and how these things move. And so the tide comes in here at the Golden Gate Bridge. This is a tidal system. We're on the ocean, but it actually behaves very differently depending on where you are in the bay. So as it goes down, you have high tide and its water is rising and pushing down. South Bay, it's very, I use the word reflective. And by that, I mean, you can tell even just by being here, so if you've spent time in South Bay, you know, it's very developed. We've really infringed on all our natural marshlands. We have development that often comes right up to the shore. We have a lot of walls. I think of it as things that are kind of hard. There's a lot of riprap. And the bay actually also, as you can see, it's kind of this weird triangle shape. So this actually ends up reflecting a lot of energy. So as the bay comes down, the tide comes down, it hits here and it reflects back up. And this is what's called a standing wave, which is kind of the same thing that if I were to snap a jump rope and you were holding the other end very taut and all that energy were to reflect, you would then have that wave come right back towards you. And so these 2 waves actually result in this interesting dynamic, which is that the tidal range, which is the difference between how intense you see that high tide and low tide, actually increases as you go south. And so if you live down here in like, let's say like San Mateo area, you're going to see a bigger difference between high tide and low tide than you do at Alameda. And this also is significant when we think about like sea level rise in the bay. And so communities down here in South Bay, they're going to experience a higher high water as we have our sea levels change. And so there's a lot of kind of coordination that needs to happen when we think about how to prepare for sea level rise. And it's very different as you move up towards the delta. This is called a dissipative tide, which just means that you can honestly kind of see from this satellite photo, there's all these braided channels. We have a lot of natural marshlands. And this would be the same thing as if I like snapped a rope and no one was holding the other end and it just sort of fizzled out. And so the tide actually just gets really, really weak. So even though there's you can barely tell there's a tide by the time you get all the way here, as compared to South Bay where we have really strong tides. In terms of water quality, those are my 2 kind of fun physical facts. The rest of this talk will be about water quality in San Francisco Bay. And I'm genuinely curious when people think about like the bay, if they think we have either like good water quality or bad water quality. And maybe won't force you guys to do a show of hands, but you can kind of think about it in your own head of whether or not you're like, oh yeah, the water quality actually is usually pretty good in San Francisco Bay. And my answer is that it actually is really good for the system that we live in. And by that, I mean, it should be way worse than it actually is. There's a ton of people that live in the bay. We're putting a ton of stuff in the water. That we have things like climate change and invasive species. And it's actually really shocking that the bay doesn't have worse water quality. And when I say worse water quality, I mean more frequent algal blooms, which I'll talk about as well. And so sort of the premise of this talk is the sort of mystery that a lot of scientists are spending a lot of money trying to figure out, which is what is the reason we have as good water quality as we do? Because we want to understand it so we can make sure we protect it, because we're a lot more resilient than we should be. And we have these algal blooms that have started to happen more and more often. So this happened in 2022. And if you're living in Oakland around then, you might have noticed all the dead fish in Lake Merritt. This was like a huge, disgusting thing. These algal blooms happen. You can see them visually in the water. They smell really bad. They suck all the oxygen out of the water. So you'll actually have fish like suffocate just swimming around. They can't breathe. It's toxic. If birds eat it, it just travels up the food web. So this is really, really bad. This type of stuff actually happens in another kind of our sister system, the Chesapeake, a lot more. And people don't really know why this doesn't happen every summer. So this was very bad that it happened in 2022, and it caused a lot of uproar in the sort of regulatory community. But scientifically, it's actually shocking that we don't have these algal blooms more regularly, and that they're a kind of rare and extraordinary occurrence when they do happen. And so there's kind of three main reasons that would cause an algal bloom to happen that I'll talk about. And there's not going to be any like satisfying conclusive answer, but maybe you can have it as food for thought. So algae is a plant, and plants kind of need several basic things to grow. The first is food. And so one thing that drives harmful algal blooms is what we call nutrients, which is kind of the fancy science word for wastewater effluent. So if you use the bathroom here today and flush the toilet, that went straight into the sewers all the way to East Bay mud where it's treated. And in a couple days from now, it will be discharged into Central Bay. And so nothing wrong with that. We have people, everyone uses the bathroom. But when you have millions of people living near a body of water, you get lots and lots of nutrients or treated wastewater effluent. And that's really rich in nitrogen and phosphorus, which might be ringing some bells if you've ever gardened. So you can think of this as fertilizer, essentially. All of our treated wastewater is essentially fertilizer we're dumping into the bay, and then we're really hoping that a plant doesn't grow. This is all the different agencies that discharge into the bay. We're all in the jurisdiction of East Bay mud. So if you've ever paid your water bill and been like, wow, I wish this was lower, I'll talk about why it's kind of high. And part of the reason that I'm actually surprised it's not higher. So it's very expensive for wastewater agencies to reduce the amount of nitrogen or phosphorus in their treated effluent. So we can treat it more, we can try to take out more and more stuff, but it costs a lot of money. And these are all publicly owned utilities. So when they do that, your rates go up. So you have to kind of think about this balancing act of, okay, we know it's bad to put fertilizer in the water, because theoretically, this is what plants that we don't want to grow will eat. But at the same time, the golden question is, how much can we put in before we get an algal bloom? And that's kind of the big scientific motivating question for these regulatory agencies, is thinking about, they have to tell these guys how much they can discharge. We have to give them a number. And ideally that number keeps water quality in the bay safe. The second is actually has a lot of historical context, which I find really interesting, which is that if you're a plant, you need light to grow. And so what that means is that you would like the water to be relatively clear. So the light can penetrate the water and you as a tiny algae can grow. The reason that we don't have more algal blooms, some people think, is because historically the water has not been very clear in San Francisco Bay. And a big reason for this is actually the gold rush. So in the 1860s, there was the advent of, it's called hydraulic mining, where people would like blast mountainsides with hoses. And this actually washed about 850 million meters cubed of sediment, so mud and sand and rock, into the Sacramento San Joaquin Delta over about 150 years. So this is like mountainsides worth of mud and water. And it means that the last 100 years in the bay, it's been really muddy. And so this is like my campaign I'm always on, which is people think of clear water as like clean water. And actually in the bay, we really like it to stay muddy, because muddy water is good. It keeps our marshlands healthy, and it also is really good for preventing algal blooms. So one idea people are having about why we're seeing more algal blooms than we used to, here's my other hydraulic mining photo, is that the amount of sediment is finally going down. So all of that hydraulic mining sediment has finally washed its way through. It's really trickled out. And this is a time series of sediment measured, I think, at the Dumbarton Bridge over the last 20 years from 93 to 2006. So you can see this yellow line, it's getting smaller and smaller. And so unless we start hydraulic mining again soon, which we really shouldn't, because it's bad for a lot of other reasons, our water is going to get clearer. And so people are worried that's going to cause more algal blooms. So we're sort of at this, oh wait, I forgot my last, this is the rogue option, which is that clams are also thought to play a big role. And this is just such a chaotic option, but it's also a very real option. So In the 1990s, a ship came in from Japan and it parked in the port of Oakland. It opened up its ballast water, it dumped its ballast water, and it was an unlucky day to have a bunch of larvae of this type of clam called Potamacorbula. And this clam, within 10 years, is now found all across the Delta, all the way in Sacramento. You can find these two species of invasive clams, Potamacorbula and Corbicula. And these are filter feeders, if you've ever had an aquarium. So they sit at the bed, they suck the water through, and they eat all the algae. And so we're sort of in this like cursed situation where we really don't like invasive species, but there's also a possibility that these clams are the reason we have relatively good water quality. I will say scientifically, it's kind of impossible to investigate this. It's very difficult to get data on clams. It's very difficult to estimate how much they're eating. You have to like dredge and then count them by hand. So we have very limited data on this, and it's kind of unclear the extent to which we should be thinking about clams. But I'll leave that there as food for thought. So I guess I'll close by talking a little bit about the sort of policy background and how science and policy intersect in a way that I think is really interesting. That's kind of what drew me to this problem originally, is that you kind of have this really difficult situation from both a scientific and a regulatory perspective, which I kind of talked about earlier, which is this idea that scientifically we really want to maintain good water quality in the bay. And by that I mean we don't want algal blooms, we want there to be healthy fish and birds, et cetera, et cetera. But it's also really hard for us to raise rates for people that, you know, things in the bay are very expensive, and we don't want to raise people's water bills and say we actually need to take a lot of nitrogen out of the water if that's not the real reason that we're getting algal blooms. What if the real reason we're getting more algal blooms is because we actually need a lot more sediment supply, and maybe we should think about undamming rivers in the Sacramento River that are trapping sediment, you know, way up near Sacramento or whatever. And so this is a really kind of ongoing question, and this is happening in real time right now. And I've been lucky to be privy to some of these conversations, but we kind of end up in this catch-22 situation where at the end of the day, if you're an agency, if you're the water board, that it's this region of San Francisco has its own water board precinct, you need to come up with a number at the end of the day, because you need to tell East Bay Mud the total maximum amount of daily nitrogen they can discharge in the bay. So this is kind of this ongoing question. And if you get, I got it in the fall, you'll probably get another, you'll get a mailer from East Bay whenever they change their rates. They're required to tell the ratepayers why their rates are going up. And so there's a lot of news articles that came out, but after the 2022 bloom, there was this huge science frenzy, and they made a decision that they're like, okay, well, no matter what, we've got to reduce the amount of nutrients coming in. Whatever magical shield has kept the bay safe from these algal blooms seems to be failing. We don't really know why, but at least one thing we can do proactively is try to reduce nitrogen in the bay. And so they made this decision. They came up with a number. Their number was a 40% reduction. And so you might have gotten a mailer. I got my mailer from East Bay Mud about 6 months ago telling you, hey, your rates are going to go up soon. And this is the whole reason why, is that they're upgrading their infrastructure to take out more nitrogen from the bay. And this was very controversial, both scientifically and politically. This is like a really difficult decision to make. So anyway, I'll kind of close with saying that I'm curious what people think of algae in the bay, or what you think we should do. I think we're very lucky to live near such a beautiful body of water. We're very lucky that it's as beautiful and as healthy as it is. And I think, you know, we have a responsibility to be proactive about protecting it. But anyway, I'll close there. Thank you. Cool. Oh yeah, question.
2 questions. So I missed one part. What was the cause of the clam?
Oh yeah, the clams. It's an invasive species. They come over in the ballast waters on ships. So ships, they when they're taking off, they take up. Oh yeah, so when they take up a bunch of water into the ship to like make it heavier, I guess, when they leave, and then when they get to a port, they'll dump all that water off when they're unloading. I actually don't really know why. It's like a ship's thing, I guess. And so if there's any sort of species or plant or anything in that water, when they dump it out, now it's just loose in the bay. So it's actually been a way that there's been tons of invasive species in ports across the world.
They basically cross the pot, like seeded.
Yeah, totally. Yeah, they just dumped it out.
They dump water, so.
Yeah, it's funny. Actually, I've spoken with the woman who was the one who first found this clam, and she had never seen it before. She's working for the USGS in like the 90s. And so she like she's like, I think this is a new species. And you know, she had to like call a professor in Japan and then like mail a sample. And this guy in Japan at a university in Tokyo was like, yep, that's a Potamocorbula clam. And now we've had them ever since.
Then I have one.
Yeah.
Algal blooms. Have you guys found, or has anyone found, or tried to have a study a byproduct that like the major byproduct that algal blooms produce? Like,
Yeah, I wish there was like an upside to them. Unfortunately, the ones that happen that are visible are just net bad. So what they do is they grow, they're very visible, and then when they die, as they decompose, they suck up oxygen.
okay, but can I one last thing? I'll show you.
Oh no, sorry, bye.
You know how we have natural forest fires,
Yeah,
and then it creates a bed of ash,
yeah,
right? There's no use for this ash, right? It's just in the way because it's like, oh, we need the natural beauty and aesthetics, but this is actually what when we get rid of that ash and we start putting chemicals on it, we impede the new seed, the new seeds. that
Yeah.
grow. So,
yeah. So algal blooms, these types are not natural. So it's not part of some like good process. The reason we're getting them is definitely there's a lot of reasons, but the main one is just that we have so many people living near the bay, and this wastewater we've put into the bay. So historically, the bay did not have nearly the amount of nitrogen and phosphorus and all these other things. That's essentially, yeah, yeah. No, it's a bummer. Yeah.
Do cities that are landlocked, that aren't near bays, handle their wastewater issues?
Most of them, that's a great question. Most of them discharge into like a body, like a river. And so we get a ton of like Sacramento wastewater regional treatment plant discharges into the Sacramento River, which flows all the way into the bay. So the bay, like it's a kind of a catch-all. So that's why it's regulated for the whole bay. So everyone that discharges in waters that flow out through the bay are subject to these big regulatory decisions, which is crazy. Yeah.
What do water treatment facilities actually do? Like when we talk about infrastructure improvement?
Such a good question. This is where it's totally out of my field. I honestly, there's people that will like work 2 offices down from me that would know the answer to that. All I know is what I learned in like a 4th grade tour where they have like the big tanks and stuff, and something's happening in there for sure.
Why are clams hard to get information like that?
Yeah, it's such a pain. It's because they're like in the sediment. So if you want to get information on a clam, you have to dredge the sediment. You have to go like a 1/2 meter deep with like a shovel underwater. So you have to have a dredger, bring it up, clean off all the mud. Then you have to count by hand and label each clam to figure out which species it is. If this is a native species or is this the Potamocorbula? You weigh them. And then you actually like cook them in an oven. It's like you get that like weight of the dry carbon. It's crazy. And then you kind of estimate how much they've eaten by how much, because you want to get off the water weight essentially. So that process, and that's just for getting like data on like an area this big. So for us to kind of have a comprehensive idea of how many clams are in like, let's say South Bay is just totally infeasible. Which is a bummer.
Can you like randomly sample various select spaces and then try to sort of
Yeah.
interpolate, or is that
They've
still?
done that. So they did that. There was like 2 sampling campaigns I've been aware of in like 2006 and 2016 or something. And the variability between the 2 was insane. So it was like, did they all die between then? It's like so unclear if the population is relatively steady year to year, or if it like varies by like up to like 10 to 100 orders of magnitude. It's just, yeah, we've got to have some clam expertise. Oh yeah.
They're like different species, or is there a limit to the species of clam that people adopt?
That's a great question. I actually don't know about the community composition. I know that there are a lot of like there actually used to be a lot of oyster reefs in the bay historically that have mostly been eroded as we've like really tried to push, development towards all the way to the bay. I do know that there are a lot of native species of clams, and there's really 2 problematic invasive species. But these invasive,
There's no ballpark figure for like in the bag, there's like maybe 500,000 different species.
that's such a good question, and I would say it's definitely less than 100.
What?
Yeah. But now I'm worried I might be wrong.
The algal bloom is caused by the wastewater, the stuff in the wastewater?
Yeah.
So if the wastewater is cleaner, would that,
That's what they're hoping, but the thing that's hard is it would be extraordinarily expensive to reduce the amount of like, I'll say wastewater in San Francisco Bay to a level where algae couldn't grow. So the best we can do is reduce it a little bit and hope that makes a big difference.
well, because I think it was Orange County that was turning wastewater into drinking water.
Oh, yeah.
So if they could clean up the water and like, we can turn some of the wastewater into drink, would that help out?
That's a great question. Yeah, so my understanding is that it's funny because when I started my job before I did my PhD, I thought of like effluent as like really disgusting, and now I think of it as like a necessary evil. In terms of the treated effluent, you can turn it into drinking water. The problem is you still have what you took out to make it drinkable still has to go somewhere. So ideally, we could give it to farmers and they could use it to irrigate their land, but realistically, we have millions of people producing, millions and millions of gallons of effluent. So we kind of it has to go somewhere.
When algae blooms like die down, do you know the reason why? Like why do they flare up but like not just stay?
It's usually because they've like eaten all the nutrients they've been able to. And then they also like start running out of oxygen themselves. So like it's usually like a big boom and bust over the course of like about a month. So it's crazy. When like one's spotted, like everyone begins freaking out, but you can't actually do anything. It's just sort of like you're watching a disaster unfold in real time where you're like, it's going to kill fish, it's going to kill birds, and it's just gonna happen a month from now. So it's a huge bummer.
Any other questions? Then let's give Sienna one more round of applause.
We can do personally in our own homes to try to.
Honestly, I should have I genuinely don't think that this issue happens on such a large scale that I don't actually have I don't think there's an easy thing that we can do. I do think it's interesting to follow this permit cycle happens every 5 years. So this last one was in 2024. The next one will be in 2029. But I think if there's another algal bloom, when you read the news coverage, I think you'll start to see a little more of this story, which will be kind of interesting, where you'll see people will be like, oh, we're going to have to reduce discharge even more. And it's always a big debate. So it is, but yeah, I don't think there's anything other than being aware of the process that comes to mind for me. Maybe you can collect some clam samples. Yeah. Thank you, guys.
Alrighty. So thank you so much for coming to August Popping the Science Bubble seminar. We will be returning on September 16th. And that one will be at the North Branch this time as we begin our tour of the various Berkeley Public Library branches. I know we have the speakers, but I don't remember. Our two speakers there are going to be talking about glaucoma and neuroinflammation and magnetogenetics, two things I have absolutely no idea about what in the world any of that means, but sounds very interesting. So turn out to the North Branch on September 16th. We'll be starting at 6 o'clock at that time because the other branches generally like to start a little bit later than this one. And if you want to sign up for any email notifications, you can do bit.ly/PTSD emails, or you can go to our website. There's a place for you to subscribe to all of our emails there as well. Thank you so much for coming out, and we hope to see you in about a month.
Thank you so much.
Oh, actually,
I actually did that.